अस्सलामु अलैकुम वरहमतुल्लाहि वबरकातुहू। डियर स्टूडेंट्स, पिछले लेक्चर में हमने ये समझा कि कोई भी बॉडी अपनी स्टेट या डायरेक्शन ऑफ मोशन खुद चेंज नहीं कर सकती है, और अगर किसी बॉडी की स्टेट या डायरेक्शन ऑफ मोशन चेंज करनी है तो उसके लिए एक फोर्स की जरूरत है। मतलब ये कि अगर कोई बॉडी मोशन में है तो उसकी स्टेट ऑफ मोशन को चेंज करने के लिए यानी उसको रेस्ट पे लाने के लिए एक फोर्स की जरूरत है। अब कितना फोर्स चाहिए एक बॉडी की स्टेट ऑफ मोशन को चेंज करने के लिए या उसको रेस्ट पे लाने के लिए, यह डिपेंड करता है कि बॉडी में मोशन कितनी है। For example, if a bullet is fired from a gun, it requires large amount of force to stop, as it contains large quantity of motion. However, if the same bullet is thrown by hand, it requires small amount of force to stop, as it contains small quantity of motion. Thus, the amount of force required to change the state of motion of a body depends upon the quantity of motion contained in the body. This quantity of motion contained by a body or in a body is known as linear momentum. So, linear momentum can be defined as the quantity of motion contained in a body. This linear momentum of a body depends upon the mass and velocity of body. For example, if two bodies of different masses have same velocity, then the body having greater mass will require large force to stop because it's having large quantity of motion due to its greater mass or greater inertia of motion. Thus we can say greater the mass of body, greater will be its linear momentum. However, if two bodies of same masses have different velocities, then the body having greater velocity or larger velocity will require large force to stop or change its state of motion. Thus, we can say greater or larger the velocity of body, greater will be its momentum. Thus, it's clear that the linear momentum of a body depends upon the mass and velocity of body. So, linear momentum is given by the product of mass and velocity of the body. That's P equal to mv, while P is the symbol of linear momentum. And linear momentum being a vector quantity, so in vector form we can write P vector equals m into v vector. And the direction of linear momentum is same as that of velocity vector. The SI unit of linear momentum is kg meter per second, while kg corresponds to m and meter per second corresponds to velocity. And accordingly, dimensions or dimensional formula for linear momentum will be m1 L1 t minus 1. Now let's come to some common terms. As we know, linear momentum or P is equal to mv. So if m is constant, then clearly P will be proportional to v. And if P is proportional to V, then the graph will be a straight line passing through origin or starting from origin. And here M being constant and can be defined by the slope under PV graph. However, if velocity is kept constant, then from this equation, momentum or linear momentum is proportional to mass. And hence the graph again will be a straight line, where velocity is constant and can be defined as the slope of momentum mass graph. However, if momentum of a body itself is constant, then we can say P equal to constant, means mv equal to constant, or simply v is inversely proportional to m. So if momentum of a body is constant, then there will be inverse relation between the mass and velocity of body, such that the graph between mass and velocity will be hyperbolic in nature as clear from the graph. अब हम चेंज ऑफ लीनियर मोमेंटम समझते हैं, क्योंकि हम जानते हैं कि फोर्स की ही वजह से बॉडी की स्टेट या डायरेक्शन ऑफ मोशन चेंज हो सकती है। और इसी फोर्स की ही वजह से किसी बॉडी की मोशन बढ़ सकती है या घट सकती है। अब मान लो हमारे पास एक बॉडी है जिसका मास m है। जब हमने इस बॉडी को इनिशियली ऑब्जर्व किया एट टाइम t1 तो इसकी वेलोसिटी u थी। उसके बाद कुछ फोर्स इस पे अप्लाई हुआ और जब उसके बाद दोबारा ऑब्जर्व किया एट टाइम t2 आफ्टर सम टाइम फ्रॉम t1 तो इसकी वेलोसिटी u नहीं बल्कि v है। And this change in velocity is because of applied force. Now, according to definition of linear momentum is the product of mass and velocity. So, therefore, the linear momentum of this body at initial state will be pi equal to mu. And its linear momentum at final state will be pf equal to mv. Now, if we take the change in momentum, that is change in momentum delta p is equal to final momentum minus initial momentum. That's equal to mv minus mu, or delta p is equal to m times v minus u is equal to m times del v. Here del v is change in velocity of body and is because of applied force. Hence, this del p change in momentum is actually because of applied force. And do remember, we are discussing classical or Newtonian physics, which assumes or presumes that the mass of body will not change if the velocity of body is far less than the velocity of light. Now, if we divide this equation both sides by the time in which this change in momentum takes place. For example, here this change in momentum takes place in time t2 minus t1, simply called delta t. Then we can write del p upon delta t is equal to m times del v upon del t. This change in momentum with respect to change in time or time interval within which this change in momentum takes place is known as rate of change of linear momentum. Now, if delta t approach to 0 means कि time interval बहुत कम है, then observation is called instantaneous observation. And under this condition, delta t approach to 0, under this condition, del p is written as dp and del t or delta t is written as dt. Therefore, our equation becomes dp upon dt is equal to m times dv upon dt. Since the first derivative of velocity is known as acceleration, therefore it's simply equal to m into a. Both change in momentum or rate of change in momentum are due to the applied force. Let us now understand Newton's second law of motion. According to Newton's second law of motion, the rate of change of linear momentum is directly proportional to the external force applied on body. In essence, dp upon dt is proportional to f, or f is proportional to dp upon dt. Or we can write f is equal to k times dp upon dt, while k is the proportionality constant and is taken as 1 in all system of units. Therefore, f will be equal to dp upon dt. But we know p, momentum, is equal to mass into velocity. Therefore, this equation transforms to f equal to d upon dt of mv. Since we are discussing Newtonian mechanics in which mass is assumed to be constant, therefore it is equal to m into dv upon dt. And first order derivative of velocity is known as acceleration. Therefore, f is equal to ma. Or in vector form, f vector is equal to m into a vector, and here m being scalar quantity. The direction of force is same as that of acceleration produced in the body. And later we can have, since we know F equal to dp upon dt, but from the concept of rate of change of momentum, we earlier discussed that dp upon dt is equal to ma. So therefore we can write F is equal to ma. Now, very important fact from Newton's second law of motion, which states F is equal to dp upon dt, and it signifies that same force applied for same time causes same change in momentum in bodies of different masses. And also the other form of Newton's second law is F is equal to ma. Now, knowing the value of mass and acceleration produced in the body, we can find the force. Hence, Newton's second law of motion measures the force. Now, let's come to the units of force. The SI unit of force is Newton. As we know, F is equal to mass into acceleration. If mass of body is 1 kg and acceleration produced in body is 1 meter per second square, then F will be equal to 1 kg into 1 meter per second square. That will be equal to 1 kg meter per second square, and that's here simply equal to 1 Newton. Thus, 1 Newton is the amount of force which produces an acceleration of 1 meter per second square in a body of mass 1 kg. The CGS unit of force is dyne, and do remember 1 Newton is always equal to 10 to power 5 dyne.